Okay, so let's get started. So last week we spent a lot of time about talking about error detection and how to achieve that through block codes of various sorts. We talked about the parity check code, we talked about the internet checksum, we talked about the CRC, talked a little bit about error models and so forth, and the general idea about error detection. So we will now take that one step further by moving up a little bit in the protocol stack and see how we can implement so-called retransmission protocols that use error detection as an integral part of their protocol, and see by how these protocols can achieve error-free transmission over networks where there will be failures, packet errors, and so forth. Okay, so going back a little bit to the beginnings about layers, protocols, and services, we know that a protocol is something that lives in a protocol layer. So in this case, we have layer n plus 1, so these are numbers. So this could be layer 6, or layer 2, or layer 3, or whatever, right? And there is a protocol entity, a piece of software, which is running at one computer at one side, and another process running at the same protocol layer at some other computer in the network, or in general, some other node in the network. And these protocols then, this protocol is executed by transmitting data back and forth here. And the data which is transferred back and forth here are called protocol data units, PDUs. So this is the abstract model of a protocol which resides in a particular layer. In practice, these protocol data units are not transferred here. This is only virtual transmission. So the real transmission is through going down in the stack at the transmitter side until we hit the physical layer, and then it's transmitted over and goes up the stack on the receiving end. Just to highlight what's going on here, the protocol data units which go back and forth here in the virtual manner actually goes down here, and when it goes down, it changes names from protocol data unit to service data unit. And then this service data unit is encapsulated in the next layer's protocol data unit. So the layer at the entity at layer n takes the service data unit that it gets from above, sticks that into one of its own packet data units, and adds some control information to that, and then transmit this in a virtual fashion back and forth between this protocol entity and its friend on the other side. Of course, this is also virtual, so actually this protocol data unit goes down here until it hits physical layer, and then actually physical transmission of these bits take place. Okay, so what we will talk about now a little bit is that this interface here between layer n plus 1 and layer n here defines a service that layer n is providing to layer n plus 1. So there is some service that this layer provides to the layer above it, okay? And the layer above it provides a service to the layer above it. So the idea is that we provide services up the stack, and we do that in each layer by using the services which are below us, okay? So we can think of it that this service here is getting refined by this layer, it's getting refined by this layer until we hit the application layer, and that's the end of the protocol stack. Okay, so services comes in many shapes and forms, and how to specify them and to say what properties they have is a big topic in itself. So some of these properties that are listed here are important, and they're also known under certain other names. But this is the terminology which is used in the textbook in this course, so let's use that. So again, a service model, one can call it, specifies the information transfer service that layer n provides to layer n plus 1. So the service model then explains exactly what that service does, right? What are the properties essentially, and maybe it's more clear here. So one such feature is the message size. Okay, so it could be, for instance, that the service, if I'm a protocol layer N, a layer N protocol, I provide the service up, right? And I tell the service above, okay, I can transmit the information to you, but I can only transfer it somewhere between 10 bytes and 1500 bytes. These are the messages that I accept, okay? So then the message size is fixed somehow, or at least limited. But it could also be arbitrary, and I'm saying, okay, no matter what you send to me, I will make sure to send it. If it's 1 gigabyte or 1 bit, it doesn't matter. I will send it, right? Sequencing is another thing, and that is basically to say that if you give me a sequence of service data units, I guarantee that I would deliver them in order at the receiving end. Or I can say, I don't guarantee that these will be delivered in order. Two different types of services. Reliability, I can say, okay, whatever service data unit you send to me, I guarantee that that will be presented at the receiving end, error-free. Or I say, nah, I'll do my best, but I can't promise anything. Okay, so either the service is reliable or unreliable. Multiplexing is a service type where I say to a number of protocol layers above me, a number of protocol entities above me, I'm willing to serve all of you at the same time. Okay. Otherwise, one can say, if I don't support that, whoever comes first, I will serve, and the rest will be blocked. Okay, so that's another service feature. Timing, pacing, and flow control has to do a little bit about guaranteeing delays over the channel. That has to do with timing. Pacing has to do with guaranteeing that if I get a sequence of packets from above with, say, 1 millisecond in between the packets, then I guarantee that this will not be perturbed too much, say. You know, maybe it will arrive slightly less than 1 millisecond, slightly higher than 1 millisecond, but it's not going to be 1 millisecond and 1 minute, 1 millisecond and 2 milliseconds, or something like that. So that has to do with pacing. Flow control is not so much of a, maybe it's a service feature perhaps, but flow control has to do with the fact that a fast transmitter can overwhelm a slow receiver. So for instance, if I have a device which is limited in some way, then a server could be much more powerful in the sense that it can transmit much more data per second, say, than this device can handle. Then the protocol must be so that it figures out what the capabilities of this device is and tailor a regular, decent amount of data per time unit for this not to be overwhelmed. So that's called flow control. Then the whole security thing, super important and getting more and more important by the day, I would say. So something called confidentiality. In the book it's called, I think it says privacy in the book. Now the book is a little bit old, so the current meaning of privacy is something different. Privacy has to do with how an ICC system in general maintains and collects personal data. So integritet in Swedish, right? Integrity is not integritet in Swedish. Integrity has to do with that the data is not changed during transfer. So whatever is transmitted, those bits are actually not changed when we get to the receiver. So this has to do a little bit, it's similar to this error detection that we did previously, but error detection that we did previously is to defend against rare and unlucky events that makes us do errors. Integrity has to do with actually protecting ourselves against a malicious user. Hacking, essentially, right? And then authentication has to do with being able to verify that a message which is received actually comes from the claimed transmitter. So when you get an email, for instance, you know that typically these are not signed, so you don't know where this email really comes from. So whenever you get an email from the White House, for instance, which I received, I don't really trust it, right? Okay. So authentication is an important thing in many applications. Okay, so here there will be a few slides now explaining more in detail what all these properties are about. But since we're lagging a little bit, I just leave it here, and then you can read here and you can read in the book. It's not rocket science, right? It's just getting used to the terminology. So this is about the reliability in sequencing with flow control, timing, multiplexing, privacy, integrity, and authentication. And now, okay, so now we're back to a little bit slower pace here. So a feature, a service feature, can be provided by implementing a protocol which is an end-to-end protocol, which means that, remember that an end-to-end protocol is that we have some end device, a host, edge device that's connected to the network, and then we have the whole network in between, and then we have another device like this. So these are the two end devices, okay? And some protocols work between end devices, and some protocols work just between the next hop, right? Hop-to-hop protocols. So one can ask oneself when implementing, for instance, error control, do we want to secure every hop in the network, or is it enough to just do it between the end source and the end device? Is it enough that we secure it here, or should we do it on each of the individual links? Same thing with flow control. Should we do that over each hop, or should we do it only between source and destination? So to make this a little bit more clear perhaps, so taking the example of error control, error detection for instance, we could have error detection working we can have error detection working on the link layer, okay? And if it does, it secures this link, right? And then we can have error control working on the next link, and error control working on the next link, and so forth. And by making sure that this link is perfect, this link is perfect, and this link is perfect, one might think that that's enough, right? That's enough to make sure that data that goes all the way down here over the channel up to the data link layer, up into the network layer, goes down like this, up here, down here, up here, down here, up here, and then up to the end devices here. It's enough to secure, to make sure that the error-free transmission over all these virtual links in one layer, and that should be enough. Actually, this is not true. And it's a little bit surprising at the beginning, because you know that the network consists of links, and if we can secure all the links, what could then possibly go wrong in the end-to-end connection? Any ideas? It's actually not very clear, so I won't hold that against you. But suppose we follow the trail of the data. It goes down like this, and then goes over the physical layer, and then it goes up into this one and down here, right? So if we have error control from here to here, that only means that the data that goes down here is equal to the data that goes up here. That is the nature of error control. However, if we have an internal failure in the network layer, maybe there is a hardware failure, or software bug, whatever. There could be something that goes wrong here. For sure, this happens all the time. Maybe it's a rare event, but for sure it could happen, right? Then, actually, errors then are introduced here in the machine itself. And it doesn't matter that the bits that goes down here are the bits that goes up here, are equal to the bits that go down here, are equal to the bits that go up here, since the error event happens inside the node itself, right? It's never protected. Okay, so for this reason, one typically always have error control also on an end-to-end protocol like this, typically in the transport layer. And by doing that, we make sure that the bits that goes down here are equal to the bits that go up here. And then we are inside the end device. Of course, there could be errors going up here and possibly going down here. But this is typically handled by the logic of the application also. Or the application itself could have some type of error control also. Okay. Questions? Comments? Clear? Okay. So to summarize, when it comes to error control, one can do that hop by hop or end to end. Okay, hop by hop is over one link. So there are pros and cons to this. So hop to hop error control cannot guarantee end-to-end correctness. Okay, so we said that. So since errors can inside a router, for instance, could go undetected. So which means that we always have some type of end-to-end control, error control, if it's important that the data is protected against errors, which is, I guess, typically the case. That doesn't mean that hop-to-hop is useless. So hop-to-hop is actually good, and in particular they're good when hops are unreliable. And that's the reason for this is that it might be, if an error happens deep inside the network here, for instance, then it might be very expensive to correct that here and then ask for a retransmission and so forth. We use a lot of network resources to correct an error which happens over one link here. So it could be useful, especially if this link is unreliable, to protect it against errors, to make sure that whatever goes down here is equal to whatever goes up here. Because then we can handle bad links or low performing links locally in the network, which is more energy efficient, cost efficient, whatever you would like to say, than to handle an error which happens end to end. Okay. So for instance, if I want to download a web page, the first thing I do here is a Wi-Fi link, and that is actually protected by error control because it's a pretty bad link, right? Which means that if errors happens here, that will be handled here locally and not by communicating with a web server on the other side of the world. Okay. So hop-to-hop error control is good when hops are unreliable, but it's less important for reliable hops, because then basically if there are no errors that occur or they occur very seldom, maybe the investment into error control on a hop-to-hop basis is just overkill. It costs more than what we gain. Hop-to-hop error control, that increases network complexity, right? Because we need more things there. As we will see, we need retransmission protocols, we need error detection and so forth. So that, which requires some computations, etc. So we don't want to put that in just because, right? We just want to put it in when it makes a difference. Okay, and then at the end of the day, it's a combination of end-to-end and hop-to-hop, which is the typical solution. And one has to trade these against each other. Okay. Right. So now let's get into how we can do error control, or how we can guarantee a reliable service. As a matter of fact, we would like to provide the following service, a service that delivers packets in order, without errors, and without duplications. Okay? So if I'm implementing one of these automatic repeat request protocols, ARQ protocols, I accept service data units from above, right? A sequence of these. And I guarantee that at the receiving end, I will deliver exactly these in order and without duplications and without omissions, obviously, right? So that's the service I would like to implement. And I'm going to use a service which is below me where definitely errors can occur. Okay, so I need to handle the errors which are happening below me. Right? Questions about this service? No? Okay. So to do that, there are some basic elements of any ARQ protocols, and there is a bunch of them already. I can say it's not just one ARQ protocol, there are many of them. First of all, we need some type of error detection, and we do that with error detecting codes, and we would like them to be good performing. Okay, and one way to say that is that they have high error coverage, which means that they can detect many types of errors that occur over the channel. But we know error detection is not perfect, so there will always be a chance that this fails. Okay? But for the time being, and at least when discussing these protocols, we assume that this happens with negligible probability. Okay? In practice, one has to design the error detection code to fit the network or the layer below me. So for instance, if I have a very bad layer below me, I need to invest a lot into the code, right? I would use a high performing error detection code. If the layer below me is pretty reliable, I don't need to invest so much. Okay, so that's an engineering choice always. Yes?
Is that like the single parity or the internet checksum?
Yeah, so exactly. So we know that the single parity check code is a pretty weak code. You know, it can handle just one error or any odd number of bit errors in the code word. But the single bit error is assumed to be the most commonly happening. Okay, so it's a pretty weak code, but it, you know, is still used, and it's used when the things are pretty reliable to start with. Where the internet checksum is a little bit more powerful, because then errors are could happen more likely, and then the CRC is even more powerful. So which one of these three to choose, for instance, if these are the three choices, depends on what you're willing to invest, and also what the reliability of the layer below it is. Did that answer your question? Yeah. Okay. Things that we haven't talked about but are crucial, we need some type of timeout here. I'll explain exactly what that means in a second. We also need acknowledgements, and these are control frames which are sent over the network just to keep things synchronized at the transmitter and receiver. Sometimes these acknowledgements, or they're called ACKs, by the way. That's a short word of it. Positive acknowledgements essentially means that, okay, I received an error-free packet, looks fine. One can also sometimes have negative acknowledgements. He's saying, oh, I received the packet, but it looks strange to me. Could you send it again? And ACKs are more commonly used than NACKs, I would say. We'll see later on why this is the case. Okay, so shall we go get started? To design our first ARQ protocol. So the idea here is that if I'm now the transmitter side, I'm serving the layer above me, so I will receive service data units from above, and my task is to transmit them securely, reliably over the network. Okay, so the first thing I do then, as a protocol entity, I accept the service data unit from the layer above me. Then I create the frame, or let's call it I will call this a frame. So this is a my protocol data unit. I will call that a frame. Okay, so from my perspective, these are this is the protocol data unit I would like to send to my friend on the other side. Okay, and I create this frame by taking the service data unit here, of course, and then I will embed that between a header and some error detection bits. Okay, so the protocol data unit would be then a header, service data unit, and then say some CRC bits or something like that. So this will be the protocol data unit that we transmit. Okay. Then this frame is transmitted, and I do that by using the service which is below me. So maybe it's Ethernet below me or whatever, I don't know. And then I start the timeout timer. And the reason for this is that the layer below me is unreliable. So will not always transmit the packet that I give it to it, not the frame that I give to it. So when I push down a frame for transmission, I start a clock, and if I haven't heard from the other side within some second or minute or 2 milliseconds, whatever it is, then I'll just assume that the layer below me has made an error, and I need to retransmit this. Question?
Trailer, is it always the error bits, or could it be something?
Nah, it could be something else. So this is just for illustration. The important thing is that we take we take whatever service data unit we do, and we calculate the control bits for that, and that is included in the packet that we transmit. Whether it's first or last or in the middle, it doesn't matter. Okay. Anyways, so this timer is crucial, right? Because if I don't hear from the receiver, then I don't know whether then I assume that the packet is lost and I retransmit it. So when the timer expires, I retransmit the frame, but I expect that if the frame goes through, to receive an acknowledgement from the other side. Okay. So this is what the transmitter does. So the receiver, okay, so now I change my focus from being the transmitter and the receiver. So the receiver is getting protocol data units from below, right? So it gets these protocol data units from below. So I wait until I receive one of those, and then I check whether there is errors in this. So the first thing I do. And if there are no errors, then I deliver the service data unit. Okay, I get the packet from below, I look at it, I check the error bits, it looks fine, then I send it up, right? And then I also send an acknowledgement back to my friend, the transmitter, which is on the other side of the network. So I inform the transmitter that I received the frame, which is error-free, and I have delivered that up to the layer above me. Okay, now if the frame here has errors in it, what do I do? Okay, well, I do the same thing, and I just throw it away. Okay, so whatever comes up from the layer below me, I look at it, and if the error bits are wrong, or if there is an error being declared, then I know some bits in the frame are bogus. Right? So what can I do? Well, I don't know where the bits are bogus, right? I just know that there are errors in this frame, and the safe thing to do is just to throw it away, right? Not trying to fix it or anything like that. I'm trying to be safe here, so I'll throw it away. And as a matter of fact, I don't know. One could think of it like I can look at this and see, okay, there are errors there, so I can request a retransmission of it. But I'm not really sure who to request a retransmission from, because I don't know if I can trust the address bits of the sender in the frame. Right? So I basically can't trust the frame. So the safe thing to do is just throw it away. Okay? Questions? No? So, I mean, here's the basic idea. So what could possibly go wrong here? Let's see. Okay, because this is a flawed implementation. But we'll see what's going wrong here in a second. Okay. So our first attempt, ARQ protocol, we're very proud of this. So let's see if it works or not. And let's see if it works on the normal operation. And it better work under normal circumstances, otherwise something is really not good. So what is normal operation? Well, normal operation is when frames can be lost. Okay, so that's the whole idea, right? That frames are lost in transmission sometimes. Acknowledgements, however, we assume that these are never lost. Okay, and we also assume that the timeout is wisely chosen. And wisely chosen is that it's longer than the turnaround time. So it will be clear what is meant with that in a second. So here we have two timelines, one for the transmitter and one for the receiver. And let's see how this exchange of protocol data units takes place on in a time diagram here. So the first thing to do is that the transmitter protocol data, the protocol entity receives a service data unit from above. It happens to be number 0. Okay. So then what the transmitter does, then it transmits this service data unit encapsulated into a frame. And let's assume that we have a header and some check bits, maybe a CRC. Doesn't need to be a CRC, but you know, in this example it happens to be. Some error detection bits here at least. Okay, and then it reaches the receiver. The receiver inspects, and yeah, I forgot about this. We also started timeout when doing the transmission. Okay, so the receiver looks at the CRC bits and compare that with the frame and sees, okay, everything is okay. So it then delivers the service data unit to the layer above it. Okay, so now we have transmitted and delivered the first service data unit. So everything is fine now. And the receiver also transmits an acknowledgement back to the transmitter. And this acknowledgement then, you know, it's a special frame that contains no user data, that is data which is valid for the layer above it. It's only control data to make sure that the protocol works. Okay, so it has a message here which is basically saying, I'm acknowledging that I received the frame from you. And actually this is important information, so we also protect that with a CRC, so that the receiver can figure out that the message that was in here was actually correct. Okay, so that was the first service data unit. Then there is the second service data unit number 1. It's transmitted over the channel, and boom, it disappears along the way. Somewhere, we don't know where, but it just don't reach the receiver. What's going to happen then is that here is where the timeout will save us. So the service, the transmitter here starts a timer that runs, and then it expires here. When it expires here and no acknowledgement is received, and no acknowledgement will be received because this frame is lost, so the receiver has no idea that it was lost, right? It's just, you know, waiting for something that never arrives. So eventually this timeout will hit, or expire, and then the retransmission protocol then retransmits that frame. And now it goes over the channel. The CRC checks, so the service data unit number 1 is now delivered, and an acknowledgement is sent. Okay, so this seems to work, right? So regardless how many consecutive errors we have, wherever the errors occur and so forth, the timeout and the acknowledgements here make sure that the transmitter and receiver are synchronized on the same page on what's going on. Questions? Crystal clear? Okay. Timeouts here, we see that they are longer than the turnaround time. So what is the turnaround time? Well, the turnaround time is the time it takes from transmission of a frame until the acknowledgement of that frame is received. Okay, so this time here is the turn turn around time. Okay, so when determining the timeout here, we need to figure out, okay, what is the typical turnaround time for the network that we have below us? Sometimes this is very predictable and sometimes it's not. So for instance, transmitting data over the entire internet, then the turnaround time is highly variable. Okay, and then therefore it needs to somehow be measured by the transmitter. Sometimes it's very predictable because it's only over one hop, for instance. Then it's basically some processing time and some propagation time, and that's it, right? Highly predictable and also quantifiable. Questions? Okay, so problem number one is that if we relax this normal operation and also allow acknowledgements to be lost, then we see that bad things will happen here. Okay, so the first thing is what has happened is that the transmitter has gotten a service data unit, has transmitted that and started the timeout. And the frame has arrived error-free, and the service data unit has been delivered. And the transmitter has then sent an acknowledgement. The acknowledgement goes here, and it disappears. So what's going to happen now? Yes?
SDU0 is transmitted.
Exactly. So the port transmitter here has no idea that the service data unit 0 has been delivered. It just assumes that it's lost and will retransmit that. What is the problem with that? Well, the problem is that it will be duplicated. At the receiving end, we would deliver the same service data unit twice. That's not what we wanted, right? That is not what we have promised. We wanted to avoid duplications. So the delivered service data units is 0 and 0. That's bad. Okay, that's not allowed. So lost acknowledgements leads to then duplicate service data unit delivery. Okay. So how can we protect against this?
Put information in the header.
Yeah. So we need to put some information in the header. Sometimes I get the suggestion, well, I mean, if you see the same service data unit twice in a row, you know it's a duplication, so you just don't deliver it. That's bad thinking, right? Because who do you know what the service data unit should look like? Maybe there is a completely legitimate reason to have exactly the same service data unit twice in a row, right? You don't know. And as a matter of fact, a protocol should never rely on the content of a service data unit in order to do its job. Okay, so that's a fundamental rule in protocols. It's also violated sometimes, right? But it should not. That we should really not do that. Okay, so and we're going back to see how we can save this with some header information later on. Premature timeouts is also a problem. So here, service data unit is transmitted and delivered. The timeout strikes here before the acknowledgements are received by the transmitter. And what's going to happen then is that the transmitter then transmits the same service data unit again, and then we get duplicates here. Okay, and so this acknowledgement for this one reaches the transmitter here. There will be another service data unit being transmitted here, because then the transmitter received an acknowledgement. Suppose this one is lost, but then it arrives a acknowledgement here, which is actually from a retransmission of service data unit 0, not for service data unit 1, but the transmitter would assume that this ACK is due to the frame it just transmitted. Okay, and then things gets unsynchronized here. So here, the transmitter will assume, okay, service data unit 1, oh, what happened? Yeah, at this point in time, the transmitter will assume that service data unit 1 was delivered and then go on to transmit the next one, which is service data unit 2, which is delivered, say, but in duplicate because of the problem with the timeout, and so forth. So if we look at the delivered service data units, it's 0, 0, 2, 2. Okay, not only are the duplicates which are bad, but number 1 is missing. Okay, not good. So what can we do about this? We can use sequence numbers. Okay, so that's basically how we do it. So we include information in the header, which service data unit, the sequence number of the service data unit. So I get first number 0, number 1, number 2, number 3, and so forth. Me as a protocol layer at the transmitter, I receive this, so I can just stick the number into my header before transmission. And then the receiver can check, do I get 0, 1, 2, 3 in that order, then everything is okay. If something arrives out of order, then something bad has happened, and we need to fix that. Okay. So the idea is that to include in the frame a number, a sequence number, that keeps track of which service data unit in the sequence we are talking about. Okay. So the main idea is that the transmitter enumerates the transmitted frames with sequence numbers, and the receiver indicates the sequence number of received frames in the AX. So when the receiver gets a frame with the sequence number, it includes that sequence number, information about that sequence number, in the acknowledgement that goes back. So then the transmitter, which receives an ACK, can look at the ACK to say, okay, and be sure exactly which packet the receiver has received. Okay. Transmitter receiver, it gets a little bit messier, but the transmitter is this entity that sends this service data units. The receiver is the receiver that takes the service data, gets the service data units, but the receiver is also transmitting the acknowledgements, which is received by the transmitter. Okay. Okay, so this bidirectional communication. Okay. Now, to keep track of these sequence numbers, to keep track of them, the transmitter and the receiver maintains state variables that keeps track of the current value of the sequence numbers. We'll see how to do that in various ways. But the idea is that me as a transmitter, when I transmit a packet, I keep track of what I just transmitted. Okay, I have a list of the packets, or the numbers of the packets that I have transmitted. And the same thing at the receiver. These are called state variables. So an example of a state variable is that the transmitter state variable is equal to the sequence number of the oldest sent frame, which have not yet been acknowledged. Okay, so it looks a little bit like a technical definition here, which I guess it is. Well, we'll see why this is a good definition to work with. The receiver state variable could be the sequence number of the frame it expects to see next time. Okay, so it's a little bit unclear why this should be a good choice, but we'll see that this is actually a good way to do it. Or rather, it's one way to do it, and this is the most common way to do it. So that's why we talk about it. So in practice, these sequence numbers, if I transmit a video or something like that of gigabytes of data, and each packet is 1500 bytes, the sequence number becomes quite large in a short time. So which means that the number of bits I need in order to represent this sequence number grows could be very large. So at some point I need to reuse the old sequence number. So basically sequence numbers must be reused. So say that I have a 4-bit sequence number, then I can enumerate 0 up to 15, but when I reach 15 I wrap around and reuse 0 again. And we will see that we can do that without any problems, as long as we choose for different protocols we need different number of bits essentially. So we'll see how to do that later on. But before going into the next step, I think this is a good time to take a question or comment. No? Okay. So let's take a break then. So 15 minutes.